Our paper for today is our last paper in this first section of class on running biomechanics and running performance. It's a 2008 paper by Scholz et al. Titled Running Biomechanics, Shorter Heels, Better Economy. It's one of my favorite papers on this topic of running performance and running biomechanics. And it's another example of the kind of titles that I love in papers where it tells you the main result here right in the title. The shorter your heels were, at least among the participants in this study, the better your economy was, the lower your rate of oxygen consumption was when you were running on a treadmill. Now, I want to make sure I emphasize what they're referring to here by shorter heels. It's specifically referring to a very important dimension of the ankle joint that's really important for human movement in general and for running specifically. And that's the moment arm of the Achilles tendon. Let me pull up my video here and give you an example of what that dimension is exactly. And hopefully everyone can see my chair there and can see my inside of my right foot here. So this is the ankle joint complex here. It's the junction between the foot segment of the body and the shank segment of the body, that articulation between those two body parts there. The ankle joint rotates roughly about an axis through the medial and lateral malleoli there. If you're not familiar with that term, if you haven't taken anatomy recently or at all. If I look at my ankle in the frontal plane here, it's got these two bony prominences on the inside and the outside. Those are the medial and lateral malleoli. And if you picture an axis running through those malleoli, that's roughly the axis of rotation of the ankle joint here in the sagittal plane for plantar flexion, pointing the toes down to the ground, and dorsiflexion, pulling the toes up off the ground or towards your nose. Okay? The shorter heels element that they were referring to in this study is this distance right here that I'm highlighting or trying to highlight here, the distance between my forefinger on the center of the ankle joint and the Achilles tendon here on the back of the ankle joint. So that distance there from the Achilles tendon to the center of the ankle joint is the moment arm of the Achilles tendon. Achilles tendon is this guy back here behind my ankle. It's in most people certainly one of the largest and thickest and strongest tendons in the body. It's the tendon for two muscles in the back of the leg here. The soleus, which is this muscle, it's one of the largest and strongest, and many people the largest and strongest muscle in the body. And also the gastrocnemius, which is this muscle up here a little bit higher on the calf. Those fleshy parts of the muscle that I'm pinching there are the muscle fibers. Those are the parts of the muscle that get activated by the nervous system and produce some forces. They then connect to the muscle fibers, then run down the leg and connect for both muscles to the Achilles tendon there, and they express those muscle fiber forces on the Achilles tendon. Tendons basically act like rubber bands. The muscles express forces on them, and the bigger that force is, the further the tendon stretches, or the more the tendon elongates. Just like a rubber band, the harder you pull on it, the further it stretches. Same deal here with tendons. They're basically rubber bands connected to our muscle fibers. Okay? That stretch in the tendon generates a tension or a force in the tendon, and it's that tension that causes rotation of our joints, or in this particular case, that tension in the Achilles tendon is predominantly responsible for this motion here, for that plantar flexion motion that I just did. Now, why is that? Well, it's just basic physics of rotational forces or moments at an axis of rotation here. You have this force in the tendon, this force along the tendon, so picture a force vector there along my tendon. And if you take that force and multiply it by this distance, by the moment arm for that tendon force, that gives you a plantar flexion moment in that direction, for you guys the clockwise direction, that will rotate the joint clockwise or plantar flex the ankle joint there. Okay? So you can also think of moment arms here of the distance between the tendon force and the joint axis of rotation as transforming the linear forces in our tendons to rotational forces or moments at our joints there. Now, what they found here in the paper was that individuals who had shorter Achilles tendon moment arms had better economy when they were running on the treadmill. And they have a picture here that may be a little bit more clear than my example there, where they have drawn on here in the black line the distances that they were calling the Achilles tendon moment arm length there. So the shorter that distance was, or the shorter these black lines were, the better the individual's economy was when they were running on a treadmill. And that's shown down here in figure 2, the main result of the study. So on the x-axis here is that moment arm length for the Achilles tendon, and on the y-axis is the running economy, or the rate of oxygen consumption when running at 16 kilometers per hour, which would be a pretty good pace to run a marathon at for most people. So the lower you are on that y-axis, the better your running economy, and the further to the left you are on the x-axis, the shorter your Achilles tendon moment arm length. Black dots are data for, I think, the 15 individual participants they had in the study, and the black line is just a curve they best fit to those data to kind of represent the average relationship between running economy and Achilles tendon moment arm length. And you can see there's a general downward sloping trend to it, where the shorter your Achilles tendon moment arm, the lower your rate of oxygen consumption, or the better your running economy was. So when you see a result like this, it's always good to, rather than just appreciating the result, even though on its own it's a pretty interesting finding, an interesting result, appreciate the result, but also question why we found this result. What are the kind of mechanical underpinnings that produce this result, or why mechanistically would a shorter Achilles tendon moment arm be associated with better running economy? That's what they spend the first part of the paper developing, and that's a good thing for you guys to always ask when you're reading studies like this. Beyond just observing the finding, try to think about or reason out, using principles from mechanics, why that finding was found, and whether it's something that mechanically makes sense or not. What they worked through here in the first part of the paper, with all these equations here, let me zoom back out, is deriving why they would expect to see this result. So they weren't finding this result and then after the fact explaining it. They went into the study expecting to see this result before they had the data on it, based on this theory here that they worked through in equations 1 through 7 here. What they were doing here is starting from an expression for the relationship between the force in a tendon, F, and the stretch or elongation of the tendon, U. This equation 1 here is basically the equation for a rubber band here. The more that you stretch, or the bigger the force you apply on a tendon / rubber band, the more it's going to stretch. Okay? If you take that equation and then integrate it with respect to this stretch, you get this equation down here, equation 2, which is an expression for the strain energy, or the mechanical energy stored in that tendon for that force, or for that given amount of stretch. Okay? If you then substitute in here our equation that I just visually showed you on my own ankle for the moment at the ankle joint, or the plantar flexion moment at the ankle joint, which again is equal to the force in the Achilles tendon times R, which is the moment arm of the Achilles tendon. If you take that equation 4 here and substitute it into these other equations up here that were produced by integrating that original tendon force equation, then you do a little bit of algebra, and you end up with this lengthy expression here, equation 7, which was their motivation for expecting the result that they saw concerning better running economy with a shorter Achilles tendon moment arm. Now, how does this equation here necessarily indicate that expectation, that the shorter the value of R here, the shorter the Achilles tendon moment arm, the better the whole body running economy would be? It doesn't indicate that exactly. What it does indicate is that the shorter the moment arm for the Achilles tendon, which again is this symbol R here, the higher the value of E is going to be for a given set for a given moment here applied at the ankle joint. Okay? And recall here, E is the strain energy, or the mechanical energy stored in the tendon for a given force in that tendon. Okay? So what they have here is an expression saying, I'm going to store more mechanical energy in my Achilles tendon the shorter the moment arm is for that tendon. So kind of two interesting things here. One, we are showing an expression here based not just on statistics or on data, but based on a simple biomechanical model that the shorter my moment arm is for that Achilles tendon, the more strain energy I'm going to store in that tendon. And we also see here that the shorter that Achilles tendon moment arm, the lower rate of oxygen consumption, or the better the running economy was. So suggesting that storing more mechanical energy in the tendon is associated with better running economy. Now, is that a mechanistic relationship, or was that just chance? Did they just kind of get lucky here? Well, can't really say for sure one way or the other. But the theory here, the plausible expectation would be that when I store more mechanical energy in my tendon, I then have more energy in my tendon to release later on in the gait cycle as kinetic energy, as energy of motion. So we can kind of think of this energy stored here in the tendon as sort of a mechanical fuel, energy that could hypothetically later on become energy of motion. And tendons, kind of like we talked about with the Pebax foam in the shoe from the previous lecture that had the very high energy return, tendons are very efficient at storing and returning energy. The energy return in the Pebax foam shoe, I think, was 87% last time, compared to like 65 or 75 in the other two shoes. Tendons are like 95 there. They're like 95% energy efficient. They lose very little of the strain energy that's stored in them and return a lot of it. So if you can store a lot of strain energy in the tendon, then that can hypothetically become a lot of kinetic energy later on in the gait cycle. Okay, more to the point here of why did this relationship turn out the way it does. Recall here that the moment at the joint, the moment that's going to rotate the joint, is equal to the force in the tendon producing that moment times the moment arm of that force to that axis of rotation. So for a given moment here, the shorter the moment arm, the more force in my muscle I'm going to need to produce that moment. Okay? And you can kind of think of the moment here as a constant. If you want to run at a certain speed, that's generally going to take certain moments at your ankle joint to move the ankle in a certain way that allows you to run at that speed. So you can kind of think of m here as being a fixed quantity. So if you are producing that moment with a smaller or shorter moment arm, you're going to need more force here, since r is on the bottom of this equation here. More force in the tendon is like more force in the rubber band. The bigger the force I apply to the rubber band, the further I stretch it, and the faster it shoots out of my hand when I release it, because the further I stretch it, the more strain energy I'm storing in it. Same deal with tendons. The greater the force that I express on the tendon with my muscles, the more strain energy I store in it, and the more kinetic energy I could possibly release when I unload that tendon. So not just a result here on moment arm length and running economy, but a theory here on why moment arm length might affect running economy, and suggesting it's due to increasing the amount of mechanical energy that a given moment at the joint will be associated with and storing in that tendon. Okay. The possible negative drawback here is that generally it costs more metabolic energy to produce greater muscle forces. Remember, these forces are, the force expressed on the tendon, but much of that force is coming from the muscle fibers, and that has an energetic cost to it. We can't produce most of that force for free. It has a little bit of a metabolic cost to it, sometimes a lot of metabolic cost to it. So generally, producing higher muscle forces is associated with a greater energy expenditure. So that's probably a factor here as well, but the data here kind of showing it's probably a lesser factor compared to the savings that you get from storing more mechanical energy in the tendon itself. Now, why is this interesting? Why is this important? What's the performance tie-in here? Well, showing that if you have somebody who's a good performer, they may have short heels here. So if you want to see if you are going to be a good runner, have potential to be a good runner, if you're not running much right now, you can look at your Achilles tendon and see if it's short or long. You know, if it's 4 centimeters, maybe pretty good. If it's 5 or 6, maybe not so good. This can also be a possible explanation for something that I'm guessing many of us have observed in sports, where sometimes it doesn't matter how hard you work, it doesn't matter how hard you train and how dedicated and focused you are, there's always going to be people, at least unless you're Michael Jordan or somebody like that, there's always going to be people who are just better than you, right? And who maybe don't train as much as you and don't take it as seriously as you, but then you both go and do a 5K and you trained your butt off and they hardly do anything and they just smoke you, right? And you're like, why can't I beat this guy? I train super hard, he does nothing. Well, maybe he has really short heels, really short Achilles tendon moment arm and is getting a boost there to his running economy that you don't get by having a longer moment arm, by having moment arms that are not so conducive to running economy. So one of those things that you really just can't do much about. That's life. Some people are just, hit the genetic jackpot and can be good at things, and some of us are not so good at those things. But possibly explaining why some people are just naturally good at certain things, such as running or such as particular sports. The other factor here is that I think this could also possibly play a role in the finding from the previous paper on the Nike shoe with the carbon fiber plate in it, in terms of explaining why the carbon fiber plate seems to assist with reducing the energy cost of running and improving the running economy. So obviously it doesn't matter what your foot looks like here, what your shoe on your foot looks like here, whether it's got a carbon fiber plate or not, it's not going to affect your Achilles tendon moment arm length there. But I think it's plausible to suspect that having the carbon fiber plate in there could affect the position of the ground reaction force along the foot, which could affect the moment that you need to generate here at the ankle joint to counteract that ground reaction force, and could affect the force in the Achilles tendon here and the storage and return of energy in that tendon, which could then have downstream effects on running economy. I'm speculating a bit there. I'm not certain what the actual mechanism would be there, but that could be something that we could possibly test in a further experiment, right? We might expect to see greater storage and return of mechanical energy in the Achilles tendon when people run in economical shoes versus less economical shoes, or shoes that have a carbon fiber plate versus shoes without a carbon fiber plate. Okay, that is it for this one, and that is it for our first section in class here on running economy. There will be a question on the first exam coming up in not this Friday, but the Friday after this Friday, so Friday of next week. There'll be two questions on the exam, one on improving performance in running and one on improving performance in jumping, which we haven't gotten to yet. In both cases, it'll be a description of a hypothetical individual who is struggling with their performance and wants to know why, and wants to know what you think they should do to improve their performance. And so there'll be there'll be a number of possible ways you could answer the question correctly for full credit. So there's no single right answer. The important part will be you have to give an answer, and then you have to support that answer. You have to explain why that's your answer. So beyond just giving the answer, the more important piece is explaining why that's your answer. And to explain why, you're going to have to refer to the references from class. So you won't be able for full credit to just say, well, I would look at their Achilles tendon and see, or Achilles tendon moment arm and see if it's long or short. You would have to say something more to the tune of, I would look at their Achilles tendon moment arm length and see if it's long or short, because according to Scholz et al., that's been associated with a running economy related to the mechanical energy stored in the tendon with each step. Okay, so just an example of what you should expect to have to do on the exams. Give an answer, and beyond just giving the answer, support why you gave that answer with references to relevant material from the readings from class. Okay, that is it for this one. We will see you next time as we jump into jumping.